All right, we're ready to start lecture B here. Lecture B, we're going to go over differential equations again. This belongs partially in section 4.4 about families of functions, but I also had to read back in chapter 6 and 11, I think, about differential equations. I will continue to assign some reading there and some problems from there as well. And I'll assign you things you can handle, okay? With some of them, I might have to give you a little extra hint, a little extra guidance, because with differential equations in general, you have to use integrals to solve them, and we don't have enough experience with integrals to fully do what we need to do with differential equations. So you'll have to get some help with them. Well, let's first review what we talked about on Monday. A common example with differential equations is modeling exponential growth and decay. The simplest kind of thing to imagine is population growth, for example. And let me re-emphasize what I emphasized on Monday. Let k be a fixed constant, and let c be an arbitrary constant. Consider the following family of functions, okay? So, using the phi symbol again, didn't have to, I could have used a different letter. It is a common letter to use with differential equation solutions, so it's worth using anyway. It's a family of functions, one function for each value of c. You can also say one function for each value of k as well, though because I'm thinking of k as a fixed constant, I'm sort of imagining not letting k change. Okay? Ultimately, though, you do want to differentiate this function with respect to t. T is time. We're thinking about a quantity like a population that's growing, say, over time. If it's population growth, k would be positive. If it's exponential decay, that's when k is negative. That's like with depreciation, for example, is exponential decay, or radioactive decay. Each individual function from this family, meaning each function where you pick a particular value c, satisfies this condition right here. Its derivative is k times itself. On Monday, I verified that on the board. I took the derivative of this with respect to t. The chain rule gave me an extra factor of k. The answer for the derivative of this is k times c times e to the kt. K times the function. It satisfies this condition. Its derivative is k times itself. It's the slope of its tangent lines are k times the output values. That's what fundamentally characterizes exponential functions. We talked about this before. We talked about the most basic example being the fact that the derivative of e to the x is itself. The slope of tangent lines equal the output values, no matter where you are. If you're at 2 or something, the slope of that tangent line, if this is y equals e to the x, the slope equals e squared, which is also the output value there. The k in this case would be 1. If k is 2, then the derivative of this function is double its output. The slope at any given point would be double the output value. The slope there, if this is 2, would be 2 times e to the 4th, and the output value would be just e to the 4th. Nothing special about the 2, I could have picked something else. It's true for all x. Fundamental property of exponential functions. And this can be reflected in a simpler looking equation called the differential equation. dy dt equals k times 1. Typically, we start with the differential equation and we work backwards. This is the model, so to speak. We're thinking about situations where the rate of growth is proportional to the size of the quantity, like the size of a population. Population is a population of rabbits. The bigger the population is, the more rabbits there are, the greater the rate at which babies will be born, right? Makes intuitive sense. Fact of life, okay? Bigger population means more babies for every unit of time. Faster rate of growth. That's certainly the simplest kind of population model. Whether it's accurate or not depends on other factors. Usually it's accurate at least over a short term. Maybe not so much over a longer term. Here's another application. Newton's law of heating and cooling. And both heating and cooling are encapsulated in one law. We'll think about it in terms of cooling. Imagine you got a coffee in the mug, okay. Maybe not an insulated mug like this, maybe a mug that's not so insulated, and it's cooling down. It's sitting in a room with an ambient temperature of R. R for room, okay? But R is a temperature. Assume the coffee stays well mixed, okay? Keep swirling it around or stirring it or something. Why? Why assume that? Because if you don't, then spatial effects come into play. Like, if you're not stirring it, the coffee molecules in the center, then there's no such thing as coffee molecules there. I don't know. The molecules in the coffee would be hotter than the molecules in the middle, would be hotter than the molecules near the edge, right? Because heat diffuses, and the ones near the edge are going to be not vibrating as fast, not having as much kinetic energy. They will be, it's a cooler temperature. But keep it well mixed, and that keeps the temperature essentially uniform. Depending on the insulation properties of the mug, there's a parameter k greater than 0 related to how fast the coffee cools. Okay, and we can draw some plausible graphs of the temperature as a function of time. T is a function of t. I love that. Capital T is a function of little t. Temperature is a function of time here. You get the room temperature. And the coffee starts out at a high temperature, higher than room temperature. It's cooling down. How does it cool down? There's different things you could guess. Maybe you think it cools down like that. Maybe you think it cools down like this. Or maybe it cools down like this. Actually, it's none of those. You can verify experimentally. It cools down like an exponential decay that's been shifted upward. And the room temperature is actually a horizontal aspect. Theoretically, that would mean the coffee never actually reaches room temperature. However, for all practical purposes, it would get to a point where it's so close you wouldn't be able to tell the difference. That's the way the coffee really cools, if you keep it well mixed. Depending on the initial temp, T0 of the coffee, it turns out a good model for capital T as a function of little t is the following family. And I'm not saying how the initial temperature fits in there. C would be related to the initial temperature. I'm not saying how. Or I could figure it out, actually. Because I could plug in T equals 0. To get R plus C e to the 0. E to the 0 is 1. So this is just a C. This is the initial temperature. I can solve that for C. C actually is the initial temperature minus the room temperature. So I could replace C with that if I wanted to. But I'm trying to initially emphasize here that any function like this will be a solution. Will represent coffee cooling in different situations for different initial temperatures. It's a family of functions. Any particular individual function in this family for any particular value of C, I'm thinking if R and K is fixed, C is arbitrary, will solve a certain differential equation. DQ for short. This differential equation right there. Why? And how is that related to cooling coffee? What does it mean for this to solve this differential equation? It means the derivative of the function, dt, isn't that fun to say, dt, should equal this thing when I replace this t with the function. Catch that? The derivative of this function with respect to little t should give me the same thing as if I plug in this function in place of capital T there. Let's see what it does. dt, the derivative of phi with respect to little t, treat the r and c as constant. The r differentiates to 0. With the other one, the chain rule gives an extra factor of negative k. That's the left-hand side of the differential equation. LHS stands for left-hand side, always for me. RHS stands for right-hand side. This thing in blue, this differential equation right here. The right-hand side is negative k t minus r. Replace t with the function, because the t is a function of blue. Negative k times capital T minus r. Replace capital T with this function that's on the screen in red there, r plus c e to the negative kt minus r. I replaced the t there with the function. The r's cancel, and the negative k comes through the parentheses to give you negative k c e to the negative kt. The exact same thing I got up there. Those are the same. These are the same. Very, very happy. Happy face. Those are the same. That means this function solves this differential equation. That's what it means to solve it. When you plug it in the left side and the right side, you get the same thing. Same functions of little t. What does that mean about cooling coffee, and why does that make sense even? What are we saying here? We're saying the rate of change of the temperature with respect to time is proportional to, with a negative constant proportionality, the difference between the temperature of the coffee and the room temperature. Think about that. What does that mean? That means the bigger the difference is, the hotter the coffee is to start with, the bigger this will be, the more negative the entire product will be, making the derivative, the slope, be more negative. It'll be a steeper decline at first when the coffee's really hot. On the other hand, if you start off with lukewarm coffee, barely above room temperature, then T minus R is small. Small positive number times negative K is a small negative number. dT is a small negative. It's a decline in temperature, but with a negative slope that's close to zero. It makes intuitive sense. This model even works for heating. So perhaps for heating, you might be more tempted to write it as in this form. That's an equivalent equation, because I just multiplied negative k by negative 1 to get positive k, and I multiplied t minus r by negative 1 to get r minus t. For heating, think of the equation this way. You got something really cold. Okay, let's not even put it in just a warm room. Let's put it in a fire. The room temperature would be the fire temperature, would be really hot. Throw an ice cube in the fire. Don't worry about phase transitions. It's warming up really quick. R minus t is really large, positive. K is positive. This product is a really large positive number. The derivative here is a large positive number, the rate at which the temperature increases for that ice cube, which essentially instantly becomes steam. It's very large. Heats up very quickly first. This is a reasonable kind of model. Again, usually you go the other way. Usually you start with the model, the differential equation, you try to figure out a solution. I'm telling you the answer first and confirming that it works. That's kind of backwards, actually. The reason we have to do it this way, at least initially, is because to go the other way, we'd have to use integration. And again, we've just introduced integration so far. Last model for today is called the logistic growth model. I don't know why it's called logistic. I don't know where that word comes from. Is are related to logarithms well in some ways. Populations often grow exponentially when there's plenty of room to grow. Right? Plenty of, cabbage and carrots and so forth for those bunnies to eat. They got plenty of room to roam and play around, and there's no limits on their population growth. However, if the population gets too large, overcrowding can become an issue. It can slow the growth. Not enough space, not enough food, predators. Well, of course, there could be predators when the population is small as well, but what's the simplest model with differential equations that can take both of these into account? Here I am going to write the differential equation first. It's a more complicated differential equation. Trying to find a solution function is definitely more difficult. We use Mathematica to find the solution. If P is the population, maybe in number of people or thousands of rabbits or billions of bacteria, and T is time, various units could be used, years, months, days, minutes. Talking bacteria could be minutes. The model we're after, the logistic growth model, says something about the rate of change of P with respect to time. I kind of just have to tell you the answer, then I'll explain it. Okay? It's going to be some constant K times P times 1 minus P over some other constant L. K and L are positive constants. Why does this model fit the first two bullet points on the screen? First bullet point says, populations often tend to grow exponentially when there's plenty of room to grow. When the population is small, when P is small, what happens? If P is close to 0, well, that's close to 0, and this is close to 0 as well. If P is close to, this is close to 1. That's what I meant to say. If P is close to 0, P over L is also close to 0. 1 minus it is close to 1. This would be small. That doesn't matter. You could say dp dt is approximately k times p times 1, which you can write as k times p if p is close to 0. It's kind of like a linear approximation. In fact, it is a linear approximation. Expand this to kp minus k over lp squared, and the linearization of that at p equals 0 will just be that. On the other hand, what if P is close to L? What is L? What does it represent? If P is close to L, then P over L is close to 1. And 1 minus a number close to 1 is close to 0. This thing would be close to K. Effectively, this thing is close to 0 if P is close to L. If P is slightly less than L, this is going to be positive. If P is slightly bigger than L, this is going to be negative, and actually the growth will be decay in that case. L is called the carrying capacity of the environment. L for limit. It's going to be a limiting value. Solutions of this differential equation, now if the initial population is small at least, will have L as a horizontal asymptote. At the start, they will grow like an exponential. But eventually, as t gets bigger, they level off. Do they ever cross L? Turns out no. They'll have L as a limiting horizontal asymptote without crossing. Not that they couldn't have crossed it. You can cross horizontal asymptotes. But it just doesn't happen in that case. It also turns out with this model, if the initial population is really high, the deaths outweigh the births, and you actually have a decay in the population toward L. Those are a couple typical solutions. How do you find formulas for functions like that? How do you solve the differential equation? And what the solutions represent and how they are used? Solutions are representing the population. The population is a function of time. You can use them by plugging in different t's, different times, to get the prediction for the future population. Let's use Mathematica to solve the differential equation. How? It's a bit complicated, but I'll explain it after I type it. DSolveValue is a Mathematica function we want to use here. There's also something called DSolve, but it's a little stranger. DSolve essentially means differential equation solver. The value part emphasizes you want the output, essentially. Type the differential equation in. Here it is on the board. Circle that, maybe put that on the camera again. I need to type the differential equation. I also need to type the initial population in some way, inside curly braces. P prime of t is a way to type in dp dt. You remember how when you use the ordinary solve command, you need double equal signs? I've shown that to you before. I didn't really emphasize it like I should have on Monday, but I put it on Moodle. Or it was in an announcement, I forgot which. You need double equal signs here too. Don't ever use single equal signs in this kind of situation. It'll mess it up. You'll have to like clear the kernel to restart again. Quit the kernel. There's a quit the kernel. Okay. The evaluation. That'll clear the memory. How do I put the right-hand side in here? Do I just type that as is? Almost. I need to emphasize to Mathematica that p is a function of t, so I type it as a function of t, like this. Okay? That's just a way to emphasize to Mathematica that t is a function of t. Then you put a comma, then you put the initial condition. Also with double equal sign. What should I pick for the initial condition? Well, I haven't picked something for k and l. I could. Let's just call the initial condition p sub 0. I can use a subscript button over here in fact and go p sub 0. Then outside the curly braces, you put a p of t, and then you put another comma t. This will solve the differential equation. Okay? It'll find a function, a family of functions that are each solutions of the differential equation. It may not look the best. There can be some things I can do to make it look nicer. Let's see how it looks. Let's see, why is it saying p appears with no arguments? I think it doesn't like the subscript, actually. Let's just do it that way, P0. Yeah, there we go. All right, that's pretty nice looking. This is a family of functions that solve this differential equation. Let me write it on the board as well. I could write it with a phi notation if I liked. And, well, phi depends on t, but it also depends on k, p0, and l. I'm not going to bother with subscripts here. Let's just say p of t. And I'm going to reorder the things on the top. P0, L, e to the kt over L minus P0 plus P0 e to the kt. Writing it by hand, I'll put the 0 as a subscript. That's one way to write the answer. It's more typical to rearrange this a little bit and maybe divide the top and the bottom by P0 and also divide the top and the bottom by e to the kt. So leave just an L on the top. This is actually a little bit more typical way to write it. What did I do again? I divided the top and the bottom by P0, and I also divided the top and the bottom by e to the kt. When you divide by e to the kt, it's the same as multiplying by e to the negative. This is plus 1, plus 1. That's a little bit more typical way to write it. Now you can graph this function for any particular values of P0, L, and K that you want, and you will get graphs based on their values that typically either look like this or like this. And you will find this function talked about in section 4.4. They even call it the logistic model. They talk about it starting on page 219 and going on to page 220. They have some graphs like that here. Okay? So this is discussed in the book, just not in the context of differential equations, though some of the things they say are related to differential equations. Okay? So I'm going to assign some problems from this section, as well as some problems from some of the later sections about differential equations. They will be things you can do, perhaps with my help. Okay? Give you some guidance on those things. I know it's difficult with all the letters floating everywhere. That was always difficult for me. Okay? So many letters, so many symbols. You can do it with particular numbers that comes up in your homework, that'll come up on the exam, particular numbers. But at least to some degree, especially for the project, you want to be able to think about it with arbitrary parameters, because that's more useful. So I'm trying to get across the most useful things. All right, see you on Friday.